Hi, this is Professor Fernandez. We're working here on lesson 6, class notes B. So let me scroll up a little bit. This example asks us to find the general solution to this, solved, and it's non-homogeneous because of the non-zero right-hand side. So let me just scroll up and remind you, I've written out the procedure here. You see in bold, step 1, step 2, but scroll up a little bit, remind you of what's going on. So the workhorse theorem for this lesson is this theorem 6.2.1. So let me just review what it says. So it says, suppose I have two fundamental solutions to the homogeneous solved version of the ODE, and let psi be a particular solution to the non-homogeneous version. So by particular solution, we mean any solution to the non-homogeneous solved. Okay, then every solution to the non-homogeneous solved has this form for some two constants. So what is basically going on here? If you've been following along with the course in the videos, you'll notice that C1y1 plus C2y2, this is the general solution to the homogeneous solved when y1 and y2 are fundamental solutions. And then psi is, as we're told, any solution to the non-homogeneous solved. So the general solution to this non-homogeneous solved, by which I mean every solution, has this form, is the sum of the homogeneous solution plus the particular solution. All right, so that's basically what the theorem is telling us, and therefore it gives us this nice little procedure for finding the general solution of a non-homogeneous solved. The first thing we have to do then is we have to find the solution, the fundamental set of solutions for the associated homogeneous solved, and then we got to find a particular solution to the original non-homogeneous, and then we assemble them in this form. Okay, so that's a quick little review of why we're doing what we're about to do. So let's scroll down here and figure that out. All right, so then when I go to solve this problem, first thing I do right here is solve the homogeneous ODE. So that's the ODE with a right-hand side of 0. So this is a CC solved, whose characteristic equation is r squared minus 4 equals 0. That factors quite nicely into a difference of, or that is a difference of squares, factors into r minus 2, r plus 2, so I get those two r values. And then each of these lead to their own solution for the ODE, which is of the form e to the RT. And then I combine these to the general solution for the homogeneous version of the original ODE up here. Great. So, I didn't have to do that last step, but I just kind of wanted to review that anyway, because this is all the information I need. I now know the fundamental set of solutions for the homogeneous version of this problem. Great. So step 2 down here is going to be finding the particular solution. This is kind of, one of the points of this lesson. I'm about to show you what will seem like a very silly way to find a particular solution, and in the next video we'll talk about a more sophisticated way. But I want to show you this way because it can be useful and save you a lot of time in certain contexts. So, I always thought finding the particular solution to these sorts of problems is bewildering because, the whole point of solving ODEs is to find the solution to the ODE. And a particular solution is, like we said earlier, a fancy word for a solution to this ODE. That's exactly what we're trying to find, so why call it something different? Anyway, but all that aside, right? The method I'm about to show you, I call very jokingly the method of staring. So it is not a very sophisticated method, but as I mentioned, it's a method that can save you a lot of time. So how does this method work? We're getting very sophisticated. What you do is you stare at the differential equation until you see a solution. So that might not be very helpful, so let me give you some more context. The point of this method is to try to extract some insights from the equation itself as to what the solution could be. All right, so on the right-hand side, we have a -4, and we're looking for the function y that solves this differential equation. And then we look at the structure of this ODE. So it's got a minus 4y here, and it's got a y double prime here. So whenever you try functions as solutions to ODEs, start with the simplest possible thing, and then get more complicated from there if it doesn't work. So I'm going to start with y equals 0, right? Does that work? And that will give me 0 here, and that will give me 0 for that term. So nope, it does not work, because 0 minus 0 does not give me -4. All right, so y equals 0 does not work. Okay, so let's try something else. How about y equals some number, possibly non-zero? All right, so if I put that in here, the second derivative of number is 0. And then this is y equals k, so I put that in there. So I'm left with the algebraic equation minus 4k equals -4. So I get k equals 1. So actually, I have found, that y of t equals 1 solves the ODE. So I have found a particular solution by just thinking a little bit about the structure of the ODE and using trial and error from the simplest functions to slightly more complicated functions. So great, so I found a particular solution. So I'm going to call this, rename it psi, so that we're using the same notation that we have been in the lesson. And then the general solution, so I'm going to write here general solution, is what that theorem that we just talked about dictates. So it is the linear combination of the two fundamental solutions to the homogeneous ODE plus psi, in this case -4. Right? So that is the general solution to this ODE.